All right, so good day to my examiners, Dr. Vira and Dr. Alpha, my supervisor, Mr. Kubun Hao, my fellow lecturers in Monash, and my fellow audience. My name is Chin Hui, and my FYP topic is soft robotic arm design for pick and place operation. So an introduction would be soft robots. Soft robots can be used for various purposes. They are made with flexible materials that can move in different directions. One of the various uses for soft robots are search and rescue, as seen in the top left GIF file here, rehabilitation, as seen in the right-hand side GIF file here, and ocean exploration in the bottom left GIF file here. Now, throughout my final year project, I have carried out literature review, which let me know about a lot of kinds of soft robots. Now, the current design of soft robot that I'm doing, which I will show you guys later, is a rather new kind of soft robot in a sense that not many soft robots that I come across in my literature review can come across as a soft robotic arm. So now we go to the project objectives. The first project objective is to study the movement of the silicon chamber for efficient material use. Next will be to design the movement mechanisms for a soft robotic arm. The designs include the structure of the overall robotic arm and the internal air chamber layout for the pneumatic actuation. The next objective would be to construct a prototype that can achieve at least 1 degree of freedom, followed by to identify the specifications of the prototype once constructed. So I'll talk about the finalized soft robot arm that I've completed this semester. The design process overview is as follows. I first start with an overall design plan for the soft robot arm, then followed by the silicon module design and simulation, then the hardware component design, manufacturing, and testing follows. So we first start with the overall design plan for the soft robot arm. I had a few ideas in mind when I was designing the soft robot arm. These three factors came to mind mainly. The first one is small scale, which means that I want my soft robot arm to be small scale. This helps me reduce the manufacturing time it takes. And because of the robot arm being small scale, it becomes easy to handle. I also want my soft robot arm to be modular. This is because that any part that has damage or is broken can be replaced easily. It will also allow the soft robotic arm to be hot swappable with different components. So let's say in a case where you might need an extension module instead of a bending module, you can do that. My soft robot arm will also be accessible, which means it is going to be easy to transport when assembled, and after transporting, it will be easy to set up also. I ended up with these parameters for my design requirements. My soft robot arm will have rotating, bending, and extending for the types of motion. Its dimensions in specifications will be 30 cm in height, 10 cm in width, and 10 cm in length. The soft robot arm structure will also include clamps and mounts to hold the silicon structures inside, and it will also be a cylindrical structure for the whole arm. Next, we go to the silicon module design. Okay, so the design for the bending module is shown here. As you can see on the left-hand side, and you can see the section view of the bending module on the right-hand side. The same thing can be said for the extension module. I'm showing the left-hand side. I'm showing the design of the extension module on the left-hand side and the cross-section on the right-hand side. The rotation module is a bit different. The sectional view now is from the top because this enables me to show the air chambers more easily. Next up, we go to the silicon module simulation. I use the Abacus CAE software to simulate the soft robot arm being actuated by pneumatic actuated. Yeah, that's more correct. For the bending module, my experimental results gave at least a 90 degree of bending. And as you can see in the right GIF file in the slide, it has a constant bending radius whenever it is bending. The extension module is also done in simulation, it achieved at least 200% extension, as seen in the slide. The extension rate shown by this module is also constant, which is a good thing. The rotation module is a bit weird. I expected it to rotate in one direction, but the simulation result showed that it rotates in two directions instead. So, in conclusion, it has a negative 95-degree net rotation in the clockwise direction. And as you can see in the GIF file here, the rotation rate of this module is really uneven. Next, we go to the hardware design of the soft robot arm. The design overview of this arm includes the mounting plates, the mounting clamps, internal supports, and mold design. I plan to have mounting plates on the soft robot arm structure to position the silicon modules and to let them position in a circular arrangement around the soft robot arm. The mounting clamps will help secure the silicon modules to the mounting plates, and they are chosen because they are uninvasive and undestructive to the silicon modules. The internal support, I plan to have it in the soft robot arm because I want it to be able to support its own weight and to also support additional payload. It will also help with the structural rigidity as well. Now, mold design is gonna be taken into more consideration because it's gonna facilitate silicon casting when done right. So here is the bending module assembly. Now there's a few components that are blocking each other in the view. So I'll show this in the next slide. I remove a few components that are repeating to show you all the different types of components that are included in this module. They are the mounting plates, internal support, mounting clamps, and silicon module. So this module in the end uses 4 silicon modules for bending. The internal support for the bending module consists of 4 components. They are designed in such a way that only allow them to bend 90 degrees. So as you can see in the section view and the covered view here, this is the case. Next up is the extension module. The extension module consists of the same amount of mounting plates as the bending module, but it uses 3 silicon modules instead. So the internal support is as shown. It is arranged in a nested position, and you can see the animation of the internal support extending in the GIF file on the right. The rotation module is a bit simpler in a sense. It only has 2 mounting plates, 2 components for internal support, and a single silicon module inside. The internal support is designed in such a way that it will only allow rotation and don't really allow any vertical translation. This is shown by the components part D and part E in this slide. Next, we go to the mold design for the soft robot arms silicon modules. There's a few steps to follow there's only 2 steps actually to follow in the mold design. Step 1 includes using the casting mode, which is part A and part B, to cast the silicon part, which is this green A here. So this is what it look like after casting. Followed by step 2. Step 2 requires 2 pieces of casted silicon, and to join them together, we use joining mode C and D to join them together. Silicon will first be applied in between the space of C and D before joining them together. The same goes for the extension module. In this case, there are more parts because the extension module are broken into 2 different types of components, which is casted silicon A and casted silicon B. So the same steps from before applies to here also, which is A, B, and D produces A here, and part C and part E produces B here. Once part A of the casted silicon and part B is completed, we can then join them together using the same method as mentioned earlier. Now for the rotational module mode, the mode design is a bit complex. As you can see, it requires 5 components to just cast the silicon part A. Part A, part B, part C, and part D of this casting mode is the outer body of the casted silicon. Part E, however, defines the internal air chamber of the casted silicon module shown here. Step 1B is a bit simpler. You just pour silicon into casting mode A and you already get casted silicon B. repeat the same method as previously mentioned, and you get the rotation module, as shown in the right-hand side picture here. To manufacture the hardware, we need to carry out silicon casting, 3D printing, and assembly of the test bench for this. The silicon casting includes mold preparation, and the 3D printing includes printing the mold required to cast the silicon and the mountings for the modules. And the test bench will include aluminum profiles and a pneumatic circuit set up beside for testing. Here is a picture of the silicon casting setup with a degassing pump, and the picture on the right shows a 3D printed mold for rotational module. These processes are quite common already, so I don't really repeat that much. I mentioned earlier the joining process of the modules. This is a more detailed look at it. So as you can see, part C and part D are joined together with a layer of silicon in between, as you can see here. Here is a picture of the manufactured silicon bending module and the extension module. After the silicon modules have been finished casting and all the 3D printed parts for the mounts and supports are complete, the modules can be assembled as shown here. There's the bending module, the extension module, and the rotation module. A total of 152 hours is needed to 3D print the 70 parts needed for all the components inside the different modules. Following this, a total of 54 hours is required to cast the silicon parts, the 8 silicon parts for the modules. Take in mind that this 54 hours is just a sequential calculation. If we cast all the silicon modules simultaneously, these 54 hours will decrease significantly. I created a manufacturing progress spreadsheet to track the type of components that are being designed and the type of components that are being manufactured. So part A here shows the individual component progress. Part B shows the progress status types for design, manufacturing, and the manufacturing status. Part C here shows the progress summary for the 3D printing parts. I didn't include one for the silicon casting because they don't really take much time compared to 3D printing. Now we go to the testing and result discussion. I use medical needles to poke through the silicon modules, which are mounted on the test bench. This enables me to control the amount of air going through the silicon module, which is expanding it. A pneumatic system is also set up with a test bench here to show the setup of my testing. Now, first we go to the rotation module. When I first tested it, it has an uneven expansion in one of the chambers. And I realized after that it's due to the uneven wall thickness during manufacturing. I also discovered an air leakage in one of the 2 air chambers. So in the end, this module didn't even move, and I didn't manage to test this module because I didn't fix it. The bending module has a better result, I would say. It achieved a bending motion of around 20 degrees. However, as you can see, it is obstructed by the other bending module, which is not actuated on the other side. So in a sense, its own design obstructed its own motion. Watching the video further, you see that I removed the internal support for the bending module, and we can see a small improvement of the bending motion with it, which is around 25 degrees. Going to the extension module, the results are quite good because it achieved a 200% extension in length. However, I realized that this motion required an internal support to work. And if I actuate the extension module without an internal support, it will just topple over, as shown in the GIF file here. So after testing, I managed to assemble the soft robot arm. And the extension module, bending module, and rotational module are shown here. They are assembled using the same components, with just one piece here being replaced and another piece here, which is the pink color part, being replaced. Here are the estimated weights of each module. The bending module is around 400 grams. The extension module is around 300 grams. The rotation module is around 340 grams. I didn't take into account their molds weight because the molds are not included inside the module components, so they are separated. And I mentioned earlier I assembled a soft robot arm. I also managed to have time to calculate how much it weighs and how much material is used. As you can see, I used a total of around 1.4 kilograms of plastic for 3D printing all the components. And I used a total of around 700 grams to cast the silicon rubber. The estimated weight of the individual modules without being assembled is around 1.05 kilograms. When I assembled all of them together into the soft robot arm, it weighs around 1.01 kilograms. The estimated parameters of each module are as shown. You can see the height, width, and length of each of the 3 different modules. The rotational module is the largest one because it's at the base, so it makes sense to have a larger size for better support. And the extension module would have the smaller size because it's on the top. The estimated dimensions of the soft robot arm is also shown here. Its dimensions are around 30 cm high and has around 90 to 144 mm width and length. I put 90 until 144 because the soft robot doesn't really have like a even width and length as they decrease as you go up. So in summary, I think that I need to include inlet and outlet in the silicon modules for better pneumatic actuation. Because I noticed that when I stop the input of air to the silicon modules, they usually take a lot of time to exhaust out. I also think that 3D printing silicon rubber or other materials with similar properties will help more because a lot of material and time have been used to print the mold for the silicon rubber. Designing a control system to achieve precise control is also preferable so that we can control the soft robot arm better. The next one would require a high performance computer, which is simulating the entire soft robot arm. So I can't really do this with my laptop, but if there's a possibility, then hopefully this can be done also. So as a conclusion, I managed to design a modular soft robot arm, which consists of a bending, extension, and rotational module. I managed to simulate and manufacture the modular soft robot arm, and also test the individual modules of the soft robot arm. In the end, I get a soft robot arm with a weight of 1.01 kilograms and a dimension of 144 millimeters in length, width, and 302 millimeters in height. So that's all for my presentation for today. Thank you very much.